Hi, I'm Antonio Navarro, and this is the presentation of our work combining dynamic concurrency throttling with voltage and frequency scaling on task-based programming models. This is the outline of our presentation. First, I'll begin by introducing motivation and the objectives we pursue, then the creation of the monitoring and prediction infrastructure, as well as how we integrated TCT and DVFS techniques into our runtime, and finally, the performance evaluation of our work. And then to finalize, I'll give some concluding remarks and speak about future work. It is no secret that the performance of our systems keeps growing, and with each passing day, our systems are getting closer to reaching exascale performance. And for already some years, this has meant that power consumption has become a critical metric in the HPC community. So from going from only focusing on performance in applications, we're now focusing on the balance between power consumption and performance. And improving energy consumption or power consumption in applications while also improving performance, or at least leaving it unhindered, is still a topic that is being studied to this day. So what do works usually use when they're trying to improve power consumption? Well, they use techniques based on two strategies. The first one is dynamic concurrency throttling, in which we adapt the number of active computing resources that we're using at runtime. So we establish a limit. The second one is dynamic voltage and frequency scaling, in which instead of limiting the number of active resources, we just tweak down their frequency, the frequency at which they operate. The most common one is DVFS for processors, but it can also work for the Encore package, for example, the frequency of the memory controller. And then we have works that also target a combination of both techniques. However, this last combination is not a straightforward task, as they are hard to mesh together, since some of these techniques depend on the workload over time and also the underlying system. So in order to exemplify or visualize it better, I've prepared this table, in which for each workload, I try to explain what strategies we will want to use: DCT, DVFS for cores, or DVFS for the memory controller or Encore. So if we're executing a compute-bounded kernel or workload, what do we want is to tweak down the frequency of the memory controller. So we would use DVFS Encore. If instead we're executing a memory-bounded workload, what we want to do is either improve power consumption using DCT or DVFS, in which we would either limit the number of active resources or tweak down their frequency. In the case of a balanced workload in which we mix both compute and memory-bounded kernels, it is not so clear which strategy to use, and we might need to combine several of them. At the same time, task-based parallel programming models, such as OMS2, have emerged as an alternative that fully yields the potential of these current systems. Currently, OMS2 has a monitoring infrastructure already that predicts metrics such as the elapsed time of tasks. And it does this so that it can create better scheduling opportunities within the runtime. So the question really is, could we extend this infrastructure with more metrics and features so that the runtime can categorize tasks in between compute-bounded, memory-bounded, or balanced? And if we could do this, it would improve our scheduling techniques or the opportunities. So our proposal is that if we want to find a perfect combination of DCT and DVFS strategies, regardless of core or Encore, we need first an infrastructure that precisely categorizes workloads based on their computational profile. Second, we need this categorization to be first online and at runtime, so that the decisions can be taken instantly. And two, with a negligible overhead in execution time, because we don't want to jeopardize performance. And last, based on this information given by the infrastructure and the categorization of workloads, we can then create heuristics that properly employ the combination of both of these techniques for both core and Encore units, and doing this in an automatic way without the aid of programmers. So in order to create a correct categorization and precise categorization of tasks, we need several metrics from several components. and the first one is the limits in memory bandwidth of the underlying system. After we have that limit, we can then compare the intensiveness in memory bandwidth of tasks to this limit. And to record or predict the effective memory bandwidth of tasks, we need first the elapsed time execution of tasks and also the number of last level cache misses. And with all of this information available to us, we can then infer other metrics, such as first the effective memory bandwidth per core, which would be computed taking the limit of memory bandwidth of the system and distributing it equally between cores. So if we take into account that all cores are being active with that memory bandwidth, we would surpass the limit. And second, the intensiveness in memory bandwidth of a task, which can be computed relating the metrics of a task with this effective memory bandwidth per core. In this figure, I show several executions of a dot product application executed with an increasing number of active cores. And in this plot, I show first the bus occupation, second, the performance yielded by the application, and third, the energy efficiency obtained. And as we can see, when we reach the 10th or 12th mark in the active number of cores, we can already see that the bus occupation is at its peak. It can no longer surpass that. And as we can see then, performance starts to not increase as much as it used to, and energy efficiency actually starts to decay. So what our infrastructure is trying to do then is categorize tasks so that we can predict when which is the sweet spot of this plot, which would be at around 18 cores. At 18 cores, what we can see is that energy efficiency can only decay from now on, performance does not increase, and the bus has been saturated for a few executions already. So once we have determined the intensiveness in memory bandwidth of our workload, which basically consists on adding up all the intensiveness of all the executing tasks, we can then decide whether our workload is highly memory bounded, highly compute bounded, or balanced. If the workload is compute bounded, what we will use is DVFS in the memory controller so we can control the frequency and due to this reduce power consumption. However, if the workload is memory bounded, we will use either DCT to limit the number of cores or DVFS to tune down the frequency of these cores. And lastly, if the workload that we're executing is balanced, we will use either DCT for cores or Encore DVFS, depending on the number of tasks that we're executing and their individual intensiveness. Before moving into the performance and power consumption evaluation, we had to assess the overhead and accuracy of our infrastructure. So we executed 9 different applications in 2 different multi-core systems. And we recorded the overhead in execution time, the accuracy of time predictions, and the accuracy of hardware content predictions. As we can see, for most cases, the overhead is negligible, and there's some cases, which is the worst case scenario, in which the overhead is still below 5%, which is the HPCCG scenario, in which a lot of fine-grained tasks are created. In the case of accuracy, we can see that the accuracy of execution time prediction is high overall, and the accuracy of hardware counters seems to be high when it's really necessary, which means for memory-bounded kernels or workloads, it has high precision, and for some scenarios, such as the n-body scenario, even though the accuracy is less than 50%, we can say that it is, we deem it irrelevant, since this is a compute-bounded scenario and we don't really need precision in these metrics, since we won't use them for our techniques. Moving on to the performance evaluation, first we decided to evaluate the DCT technique, comparing it to the vendor OpenMP implementation and the OMS baseline implementation. And as we can see, the performance is unhindered for most of the benchmarks, and there are some cases in which it's a bit better and some cases in which it's slightly worse. So we can say that overall the performance is unhindered. When it comes to power consumption, however, we can really see that there's a benefit when limiting the amount of or number of active cores. Afterwards, we evaluated the performance and power consumption of our DVFS techniques. So we compared the OpenMP vendor implementation, the OMS baseline, DVFS core and uncore, and DVFS uncore using DCT for memory-bound workloads instead of DVFS core. As we can see, the performance overall is the best performance overall is obtained using DVFS uncore plus DCT, which is the one that leaves performance unhindered, and in some cases, such as mini-MR, improves it substantially. When it comes to the normalized energy gains, we can see that overall the best option to use would also be DVFS uncore and DCT, in which we see power consumption reductions over all benchmarks. In this summary, we plot the energy reduction gains of our final heuristic, which is DVFS uncore plus DCT, when compared to the best static configuration using any kind of DCT or DVFS available. And as we can see, it has competitive energy reduction when compared to the best static one. In order to better comprehend where the benefits of the previous scenario in mini-MR came from, we decided to perform an in-depth analysis by plotting the CPU utilization over time of those executions. And as we can see, DCT is acting in the bottom part by limiting the amount of active CPUs, which in turn improves performance and power consumption. We also extracted the average CPU utilization over time, and we can see that it's 3 points in CPUs lower than the baseline version in ohms. So as we can see, while performance is unhindered, energy consumption is improved. So to conclude our performance evaluation, we could say that DVFS and core combined with core DCT yields the best benefits out of all the combinations we tried. And we can also say that even though it's a tedious task to combine both of these techniques, our analysis shows that it can provide up to 15% better energy efficiency overall in average, regardless of systems or workloads. Furthermore, employing techniques such as DVFS in other resources, such as we've seen in Uncore, or it could be some like accelerators, could benefit other systems like heterogeneous systems. Also, hybrid applications could also benefit from system-wide scheduling techniques that take these workload categorization and these techniques into account. And this concludes our presentation. Thank you very much.